This works, yep. All right, good morning. Let's continue with, actually finish off the reactions of alkenes. So we looked at osmium tetroxide last week. And osmium tetroxide converts alkenes to 1,2-diol. And the mechanism is a cycloaddition. And we'll see very similar mechanisms in the next two oxidative conversions. But just to summarize, what you get from the treatment of an alkene with osmium tetroxide is the 1,2-diol. And again, the hydroxy groups are from the same phase of the alkene. It's a syn addition across the alkene. We can also take alkenes and completely oxidize the carbons, the sp2 carbons, by using a more powerful oxidant. That's potassium permanganate. And potassium permanganate does a complete oxidation to give either ketones or carboxylic acids. So that's the conversion. We'll talk about the mechanism in a minute that you can affect with potassium permanganate. So it's a more vigorous oxidation of the carbon-carbon double bond. And then finally, another oxidation to look at today is the conversion with ozone. So the ozonolysis, again, we use an oxidizing agent. Agent is in this case O3, the molecule ozone, it's a gas. And under conditions of ozonolysis, we also convert alkenes. In this case, we get ketones and aldehydes. And again, we'll look at this mechanism in detail before we go over to look at the oxidation again and oxymercuration reaction. You see here on the slide, the PowerPoint slide that I projected, see the chapters that you should look at. So we'll look at oxidative conversion reactions, then ozonolysis, oxymercuration, epoxidation. And finally, we'll end up with hydroboration reaction, which is this two-step conversion of an alkene into an alcohol. Okay, but let's focus first on the next oxidative agent here in our list. That's potassium permanganate. Okay, and on the summary here, you already see that there's a reason why we have three different reactions, because we get different types of products. So when we look at propene, and we use potassium permanganate, and we usually use an aqueous solution and also add some base. For example, sodium hydroxide. So those are the typical conditions of potassium permanganate reaction. You can also do reaction with acid. For example, sulfuric acid, that gives you the so-called purple sulfuric acid. It's a very interesting reagent. It's also a very explosive type of reagent. So you want to treat the potassium permanganate with basic aqueous solutions. That gives you a more stable reagent than if you use acid. But for some conversions, if you're careful enough, of course, working behind a shield, you can also use the so-called purple sulfuric acid. And the reason, the name for the purple sulfuric acid comes, of course, from potassium permanganate, which is a deeply purple crystalline substance. So under these conditions, what you get from this olefin here would be the corresponding ketone, or in this case acid actually, acidic acid by cleavage of this. And we also actually get CO2 upon complete oxidation here. So let's look at the mechanism of this conversion. It's a cycloaddition, very similar to the reaction that we have seen with osmium tetroxide. We have here the potassium permanganate, MnO4 minus, potassium is the contraine, and we get the addition across the double bond. And the driving force is the reduction of the high oxidation level manganese. So that gives us an attack from one phase of the element. So the new bonds are both formed from the same phase. And now, since manganese is the stronger oxidant than osmium, we get an additional fragmentation reaction that breaks the carbon-carbon bond. Okay. You can see this flow to the manganese happens again here, and as a result, we have now broken the bond between the original alkene sp2 hybridized carbons. That gives us two molecules, both of them at this stage, two aldehydes, formaldehyde and acetaldehyde. And formaldehyde is further oxidized to carbon dioxide via formic acid. And as you can see, formaldehyde, acetaldehyde is also converted to acetic acid. With additional potassium permanganate, of course. Now we'll look at the mechanism of the acetaldehyde oxidation. With potassium permanganate as an example. And so the first step here is the reaction of acetaldehyde with base of water. It's a reversible reaction. And it's a nucleophilic attack onto the carbon. And it's a reversible process. But that gives us another alkoxide here that now we can convert to a manganese derivative using fresh reagent. So using more of the potassium permanganate, we can now formulate that this negative charge attacks on manganese. So we get this intermediate where we have made a new bond between the oxygen atom and the manganese atom. And again, manganese is very electron destroying. So this one of the alkoxides that are ligands on the manganese can now grab this proton. The electrons flow into the carbon-oxygen bond, and that allows the oxygen-manganese bond to be cleaved heterolytically, again pushing the electrons into the manganese. And from here on, if we want, we can also distribute them further onto the oxygens that are attached. And of course, the oxygen on the manganese make it so electron withdrawing. So this gives us acetic acid, which is our product. Put up on the original reaction sequence here. So here we end up with acetic acid. And also, of course, we get a manganese salt side product. If you want to draw this out, then one of the ways, one of the resonance structures to draw it would be to draw this structure. And if you track the oxidation level on manganese, just to illustrate that in fact we have reduced the manganese, when I start here, I have an oxidation level of +7. +7 on the manganese, and down here I'm on +5. So formally I have reduced the oxidation level down 2 steps to from +7 to +5. And of course at the same time I have oxidized the carbon now from a +2 oxidation level to a +3 oxidation level. So that is the mechanism of the second conversion. So we have really 2 mechanisms here. We have the original mechanism for the attack here, which is very similar to the osmium tetroxide, very analogous. Of course, osmium tetroxide has an additional double bond to the oxygen. It's an osmium 8 complex. And that gives us this manganese diester. When we have the osmium step, this is hydrolyzed, but with manganese, the electron destroying effect of the manganese alkoxides is stronger, and so we fragment the carbon-carbon bond, pulling more electrons into the manganese. That gives us these aldehyde intermediates. Aldehydes because they both have hydrogens attached at the alkene, and then both of these are further oxidized. In the case of the acetaldehyde, we go one more oxidation step to the acetic acid. In the case of the formaldehyde, which I haven't drawn on the board, we would actually go even further. We would get formic acid, and formic acid has still a hydrogen attached to the carbon, so it can be ultimately oxidized to carbon dioxide, even an oxidation level higher. So we can go all the way in the fragmentation, the breakdown of this precursor. So it can be a very useful method if you have access to a relatively cheap alkene and you want to make the corresponding carboxylic acids, and you just degrade them with basic potassium permanganate. So that gives us the second of our conversions, much higher oxidation than the osmium tetroxide, and then ozone is somewhere in between, because here I write down ketones but as well aldehyde. So this means that ozone actually stops in general at the step of an aldehyde, versus obviously what we have here with potassium permanganate, we have a further oxidation which is just as fast as the original oxidation. So we cannot stop the potassium permanganate oxidation at the aldehyde stage, because this is the rate of oxidation of the alkene is very similar, or actually lower than the rate of oxidation of the intermediate aldehyde. So with ozone, we get a slightly different distribution. It's a milder oxidation. So we can look at this and maybe notice where the differences are that explain the intermediate isolation of the aldehyde. So let's look at the mechanism for ozonolysis. And I'm using a cyclic alkane here as an example. So let's use methyl cyclopentene. The structure of ozone is a little bit unusual as well. I think you all know about ozone, but maybe you haven't thought much about its structure. The Lewis dash formulation is not the greatest for drawing ozone. You actually have to put in charges, and so usually it is drawn in the way I put it on the board, with an oxygen that's positively charged in the middle, and then a thermal oxygen that's negatively charged. But there are other resonance structures that explain ozone. As you know, ozone is a reactive compound. It is in the atmosphere, protects us from UV radiation that hits the Earth, so it can be very useful because it traps radiation. But if we breathe it down here on Earth, we also can get all kinds of side effects, health damage if you expose it to much ozone. So ozone is a very toxic gas. One of these chemicals that has both positive effects in the ozone layer, of course, of the atmosphere. But again, if you breathe it, then it's very toxic. It's very reactive. And so it reacts with alkenes in a mechanism that's again extremely similar to what you've seen with osmium tetroxide and potassium permanganate. So the reason I put these oxidations together is to show you the same principle being applied again and again in the initial functionalization steps. You see all these analogies, essentially only the central atom changes from osmium to manganese to oxygen here. A very similar pattern, even though we're talking very different positions in the periodic table and ultimately very different molecules. So osmium tetroxide is a liquid, ozone is a gas, and potassium permanganate is a crystalline solid. They also have very different physical appearances. So once I get the addition product, I end up with the mole ozonide. And again, the stereochemistry is very well defined. It's the syn addition in the hydrogen here. So we get a syn addition. Across the double bond. And we get this intermediate, which looks very dangerous. The mole ozonide. And it's a very reactive compound, and so it decomposes in situ. And that's the good news about this compound, actually, and I'll get back to that in a minute. So this compound fragments, and it breaks the carbon-carbon bond. So it's somewhat related to get an intermediate mechanism between the osmium tetroxide and the potassium permanganate. And again, I'm now fragmenting this molecule, giving more electrons to the central atom, in this case the oxygen. Again, try to see the parallel features of these mechanisms. It's very important that we learn how these organic mechanisms really have a common theme, because you'll see a lot more mechanisms in Chem 32 as well. Once you start realizing that there really isn't that much of a difference, you can change atoms, stereochemistry and so on, but the principles are the same. It will become a lot easier to learn these different mechanisms. So it's a fragmentation here that occurs. And now in this case, of course, we don't get two molecules, even though we break the CC bond, and that's because we still have the 3-carbon tether that holds the two ends together. And so now we end up with a ketone from the top system here, and we end up with a very interesting, again, not very stable looking intermediate at the bottom, and we still have an oxygen-oxygen single bond here. And so this compound is again unstable, but also usually is not isolated because it reacts with itself very quickly and generates the ozonide. And the ozonide comes by a simple addition reaction. I'm drawing the arrows here. See, again, I'm kind of annihilating the charges here. Looks a little bit complicated, but trust me, those electrons find each other. And then the product shows, I think, more clearly what the system is here. So this is a bicyclic compound now that has an oxygen ether bridge at the top, and then it has the peroxide function at the bottom. And this is the ozonide. And then this part here that I circle here, this is a peroxide. And so this compound now unfortunately has very bad intermediate stability, which means it's stable enough so it can be isolated. So you can take this reaction mixture, happily remove the solvent here, and on a rotatory evaporator or a distillation, you can concentrate it, you can put it away, forget about it for 2 weeks, and then suddenly it blows up. So it's a very explosive compound of intermediate stability, and that makes it very dangerous. So this is very hazardous, dangerous, because it is a strong explosive. But again, it doesn't decompose spontaneously immediately. You might think it's okay, you can stick around for a few days, a few hours, a few minutes, a few weeks, even a couple of years before it finally detonates for some reason. It might have been hit by the photon, somebody might have shaken, something might have crystallized out there that provides a sharp surface, an edge where you can actually find some energy to start the detonation. So once you start eliminating oxygen from the system, you oxidize it, the peroxides fall apart, and there's a catastrophic chain reaction occurs that leads to a lot of energy, and they usually refer to that as an explosion. So you have to be very careful with this. And so the best way to deal with this is generally to have an immediate reduction. And there are a lot of reducing agents, and very popular ones, just adding some metal zinc powder together with a little bit of acid. So let's use a little bit of HCl and water. And so this is the reductive workup. And so I'm telling you this because, again, sometimes people underestimate just how a very small amount of compounds can be very dangerous. And so you're doing a reductive workup immediately without isolating these compounds. And that's the safest way to deal with it. And the reducing agent, this could be catalytic hydrogenation, a catalyst, palladium and hydrogen gas. It could be sodium borohydride, or it could be zinc HCl, which is a typical reducing agent. And so in the reductive workup, you then cleave the oxygen-oxygen bond reductively. So we'll draw that intermediate. And of course, this is all connected to zinc, and it's protonated. So I'm going to draw one of these already protonated by the acid as an OH. And then we just fragment the system. Okay. And so that gives us the two carbonyl compounds. I'm going to label, there's a color here, there's purple, the two carbons from here. There's one, and then there's the other one. These are these carbons here. And so the top carbon has a methyl group attached to it, that's here. And then the bottom carbon has a hydrogen attached. That's why this is an aldehyde. So this is the ketoaldehyde product. And again, these two functional groups are connected only because there is a tether. So there's a tether here of 3 methyl groups that comes from our precursor system, the cyclohexane. Okay, so now we know why under these conditions you don't get oxidation of the aldehyde. The reason is that the aldehyde is only formed in the reductive workup. So we don't have oxidative conditions anymore. If we had any kind of O3 left, that has also been quenched when we added the zinc to that reaction mixture, right? So all the ozone has been destroyed by the reducing agent as well. And of course, we reduce the peroxide. So not only do we make the reaction workup safer because we reduce the reactive functionality, we also protect the aldehyde from further oxidation. So there's no aldehyde formed in the ozonolysis of the intermediate, but of course you do form the aldehyde in the potassium permanganate, and so that can react further. So the major reason why why the ozonolysis is protective of aldehydes and can isolate it if you don't get the acid, is because the aldehyde is normally coming up after we have already destroyed the ozone, the oxidative agent here, and so there's no chance for the ozone to go back in and oxidize aldehydes further up. Okay. Any questions regarding the three oxidations? So today we discussed the two of them, the potassium permanganate and the ozonolysis. Again, note the similarities in the mechanisms. Some, of course, specific features that are typical, and that's why we get the different products, the three different classes of products, the diols, the ketones, carboxylic acids, and then the ketone aldehydes, or also dialdehyde, of course, if you had an unsubstituted cyclopentene here. If you would take this and put a hydrogen here, you would have two aldehydes. That could be really process. So any questions regarding the oxidation? So a lot of mechanisms, but they are similar. It's important that you practice them. What about the significance? Well, osmolation is pretty important, so usually that's something that shows up in exams. And certainly ozonolysis. Ozonolysis is an organic chemist's favorite. We always like ozone, we like the reactions, the mechanism involved, so definitely put some kind of note there that this is a good candidate for the final exam, or a mechanism, or also for conversion. We gave you one additional example to think about before we move on to the other oxidations, the remaining oxidation in our list. Okay, so look at this system and try to predict potassium permanganate oxidation and what would happen, what kind of product would you get. So spend a minute thinking about the reaction of methyl cyclohexene with potassium permanganate. Try to predict the product. Same conditions, basic conditions here. So what is the product? Of this process, it's very similar to the ozonolysis starting material, right? You just add an additional methylene group, the ring is larger. What is the product you will get with potassium permanganate? Anybody can tell me right away? What is the product? Yes. Okay, so it's a keto acid, right? Keto acid. Ketone, methyl ketone, 1, 2, 3, 4 methylene groups, and then here we have the carboxylic acid. Okay. So that's the cyclic alkene equivalent of the ozonolysis of cyclopentene, again with an additional methylene group tethering the two functionalities. You get the ketoaldehyde in the ozonolysis, and you get the keto acid in the cyclic alkene for the potassium permanganate reaction. Okay, everything clear, or does anybody have any questions? Okay. So let's look at the oxidation. We've already done that. We have been there, and so this is a review. NCPEA, metachlorocarbonzoic acid, remember? And just an example here of what we can do. Let's again take our methyl cyclohexene and we treat it with MCPBA. Let me do the mechanism here. acid. And we're going to do the mechanism. So we shuffle around the proton, essentially attacking the terminal oxygen. We break the oxygen-oxygen bond. Again, that's a peroxide bond, similar to ozone. We see the reactivity, these bonds. And here we get the product, which is an epoxide. Throwing in the hydrogen to show that we have a syn epoxide. And of course, we get the product from the reagent, which is now a standard acid without the peroxide function. So metachlorobenzoic acid, not parabenzoic acid anymore. And again, this is the mechanism of the insertion of the oxygen atom here into the carbon-carbon double bond. So this is the epoxidation reaction. And that's something that, again, we looked at in the last chapter already, so this is a review. What is not a review, what is new here, is the next reaction, and that's the oxymercuration reaction. And the oxymercuration reaction essentially allows you the Markovnikov addition of H2O onto an alkene, giving you an alcohol. So overall, this is a Markovnikov hydrate of an alkene. So if you look at a particular substrate, and we have methyl cyclohexene, let's use that again. We use a mercury salt, let's use mercury acetate. And we do this in an aqueous environment. And as you will see, it actually has two steps. Second step is a reduction, sodium borohydride, which we do in an alcohol solvent. Let's use ethanol for that. And the overall addition is a Markovnikov addition, so we end up with this alcohol, which is a tertiary alcohol in this system. So it's a Markovnikov type hydration in two steps. The first one is the actual oxymercuration reaction. The second is again a reductive workup with sodium borohydride. So this is another example for taking, and in this case, a toxic compound, not an explosive one, and doing a reductive workup. That gives us the product. And of course, we'll look at the mechanism. Okay, so remember the bromination. This is a related mechanism to the dibromination of alkenes, or the bromination of alkenes is Br2. So if you want to make a little footnote in terms of the similarity, go and check the dibromination of alkenes, and we see similarities. Our mercury acetate, and mercury is very polarizable. It's relatively large metal, has lots of d shells, And so it can easily bind to the pi system. It's again the presence of the pi electrons in the alkene that makes this reaction go, that attracts the mercury, the heavy metal here, to coordinate with the alkene because of the donation that the filled pi orbital can give into the empty d orbitals of the mercury. So we're kicking out formally a ligand of mercury, which is an acetate, by replacing it with the alkene as the new ligand. And I can attack from either face. I'm just choosing now, in this case, the bottom face. Generating a positively charged ion. Remember the bromonium ion, so this is the equivalent of the bromonium ion with mercury, and this is known as the mercurinium ion. Okay, so this is the mercurinium ion. And we have a counter ion here, and that of course is our acetate. And now this is being attacked by water, because water is in excess. We have a lot of water, that's our solvent. And where do we attack? Well, it's very similar to the attacks we've seen on related species, like the protonated epoxide, like the bromonium ion. Again, the similarity is that we attack at the weakened bond. So this bond is weakened because it gives us essentially an access to a tertiary cation. So this bond is weakened or elongated. So this bond becomes the natural place for the water to attack. And then of course the electrons flow onto the mercury. And they compensate for the positive charge there. And we have a positive charge on the water. I can use the negative charge on our acetate to compensate for that. And I'll continue with the mechanism on the board on the left. See, the stereochemistry is very defined by the attack anti-is a two-type attack that I have onto my mercurinium ion. So this is an SN2 reaction. SN2 process. Okay, and that's our intermediate. So the good news, there's a stable intermediate. It can be isolated. The bad news, it's very toxic. It's an organic mercury compound. You do definitely not want to have that in your body. because the mercury reacts with all kinds of biological macromolecules. So we're going to be very careful with this, and again, the best way to deal with it is a reductive workup. So now our sodium borohydride comes in. And the sodium borohydride reduces the mercury, interestingly. And there's various ways to formulate that. So I'm now going to give you my explanation, my mechanism, but you'll find different mechanisms in the literature. So I'm giving you a relatively straightforward mechanism, which is reasonable, but there's more than one possibility for the second, the downhill reactions from the mercury compound. I'm making this interesting mercury hydride by displacing by an SO2 reaction our acetate on the mercury, and then this compound, that's what I would call a reductive elimination. And eliminates mercury metal. And of course gives us our product. So the mercury metal is real. I have run this reaction, and even if you don't know anything about the mechanism, it is a striking reaction because you end up from an organic mixture in alcohol and ethanol, you end up with little mercury pellets in there, mercury spheres. So you get liquid mercury in the reaction. So it's very nice actually to see that you form metallic mercury. Mercury is here in this process. There is some disagreement about the mechanism, that probably more than one mechanism is feasible. You can also formulate this via a radical mechanism. What I'm giving you is the reductive elimination mechanism, but there's a radical mechanism, a radical chain mechanism that's also feasible. So what I gave you here is a reductive elimination, or an ionic mechanism. You can consider this also an ionic mechanism. That's one possibility. But the end product is the same. You end up with this tertiary alcohol, which is a formal addition, hydration of our double bond. So I hope you noticed that I get the enantiomer. I believe I got the enantiomer what I drew originally here. Yep. But of course these are not chiral compounds. It just looks like the enantiomer, so this is actually achiral. And so what I drew over here is identical to the product I drew originally here, because we have two identical substations. So it's a flashback to stereochemistry, right? This, even though this looks like a stereogenic carbon, it's not stereogenic because the two substituents here are identical. So this is an achiral molecule. If I drew the same molecule, I split it essentially 180 degrees. Any questions to the oxymercuration? So it's not that difficult, right? The mechanism. Straightforward. So, reduction step, mechanism there is a little bit still elucidated or unclear. There's probably more than one mechanism. I gave you one, there's also radical chain. But essentially it means, you're probably not going to be tested on that because there's several possibilities. But I gave you one. You'd like to see a mechanism or the second step. What's important is that you know what the product is. Essentially this sequence that I drew up here. And you know what the reagents are doing and how you end up with the product. But the mechanism of the second step or the reduction step is not so significant. The first step, however, is significant, and it ties into the bromination mechanism. So the two are very, very closely related again. Okay, so at this point, there are no questions. Are there questions? The obvious question would be, well, how would I do the opposite of this? essentially getting the anti-Markovnikov product, right? That's what you're interested in. How would I get the anti-Markovnikov hydration? How would I get that? And of course, there's an answer. How could I not give you the way to do this? This is via hydroboration. And so we'll look at hydroboration here as the last chapter, or last paragraph here in the reaction of alkenes chapter 12. So hydroboration is up, and that gives us the anti-Markovnikov hydration. Okay. And so hydroboration was invented, studied by one of the more famous chemists, and his name was H.C. Brown. And he got the Nobel Prize for his contributions to hydroboration. So it's a very significant, again, very important chemical transformation. And I heard one of his lectures, and he said that people ask him why did he start to do boron chemistry one time ago, because nobody did boron chemistry. But he picked it up, and he said he just kind of followed his destiny, because his initials were hydrogen, carbon, and boron. So you can check your initials right now and figure out what kind of chemistry that destiny, fate wanted you to do. Just check your initials, check for the elements, and then you know what you're supposed to do in the future. So he did the chemistry of hydrogen, carbon, and boron, and he got him the Nobel Prize and lots of recognition in this field. So HCB. I actually checked that. And this phosphorus and the tungsten, I didn't do much phosphorus chemistry, almost no tungsten chemistry. I didn't really follow my fate here, but maybe I still have time to go back to the rules here. But check your initials for the element, because at least in one case it worked out very well for one guy. Okay, hydroboration. Let's look at the product again, the sequence. And by now, since we've used this quite a bit, let's use our methyl cyclohexene, and you can compare different products this way, very linear, but of course it applies to a whole bunch of different alkenes. So if you do a hydroboration here, we will have to use borane, and let me at this point just use borane as pH3, and I put that in quotation marks because pH3 really doesn't exist. Okay. But I'll get back to that on the reagent discussion. And then I need a second step again, that's why I have a 1 here. And in this case, it is hydrogen peroxide together with sodium hydroxide in water. That's being used in the workup, and so now this is an oxidative workup. That's different, of course, from the two reductive workups that we have looked at. Okay. And that gives us the product here of the hydroboration, and lo and behold, that is an alcohol that is now the anti-Markovnikov product. And this compound now is chiral, but of course in this reaction I would get the racemic mixture. So I would get the other enantiomer to the same extent. So I'm writing here in parentheses that this is obtained as a racemic mixture, but we only get the trans alcohol. So very important here is the fact that these substituents are trans, or anti. Okay. So we get a single stereoisomer, we don't get the cis. Okay. So I'm writing here no cis. Only trans. It's racemic, but it's a defined diastereomer. We only get the trans or the anti-diastereomer. And of course, we'll look at the mechanism. So the mechanism of hydroboration. So the first thing we have is an addition reaction, just as we had always in these systems. Again, the pi system looks mighty attractive because of the electron distribution. And so we add boron across the system. And that is a syn addition. So from the same phase. So putting the hydrogen and the boron onto, in this case, the bottom phase. But of course I could attack from the top as well. And that gives us the borane intermediate. And this is an organoborane. Organoborane intermediate. Okay. And this can react on, but for right now we'll only consider the reaction of one of the borane hydrogen bonds. But in fact this has still two borane hydrogen bonds, so the same mechanism could have happened 2 more times. Depends on how much excess of the boron we're using. So right now, using a slightly simplified mechanism, assuming an excess of borane. So this sits around without adding across other double bonds, which it definitely could. So we can do several things with this. This is a pretty nicely behaved intermediate. One of the things we can do is, for example, treat it with acetic acid to quench it. And if we want, we can use deuteracetic acid with a deuterium isotope label, and that gives us a way to introduce specifically a deuterium. So we can make isotopically labeled compounds. So this is a deuterium labeled product. That's very similar to another reaction we've seen in the Grignard chemistry or the magnesium chemistry. That's the Serevitinov reaction, right? So again, invite a little footnote here, go back and look at the Serevitinov reaction. It's a very similar process. But more interestingly, and leading us to our alcohols, is the treatment with an oxidative reagent, oxidative workup with hydrogen peroxide. And remember, we also have base here. So hydrogen peroxide is a very good nucleophile, much better than water. And it adds onto the borane. And remember, the borane only has an electron sextet. It's an electron deficient. It is a Lewis acid. So it readily attracts electron pairs or Lewis bases. So this is our adduct, and I now have a negative charge on the boron, but the boron now has an electron octet. So we started out with an electron sextet on boron, and now we have an electron octet. And that takes us back all the way to the beginning of the octet rule, right? You can see how we're starting to put concepts together here in the lecture. So a lot of things will come together. This is a flashback to the very basic electron configuration discussions we've had. We also need to get rid of this positive charge here. I'm now taking this OH minus, go all the way down here to pick up the positive charge. At the peroxide. Redrawing this, I now have a system that has the peroxide bond. I'm going to highlight the peroxide bond. So this is a hydroperoxide. In principle, a dangerous system, but again, it quenches itself, and it does so by migration. And so your footnote there is, look at Wagner-Mirvine rearrangement or carbocation rearrangement. Very similar to that. And the bond that migrates is the bond to the boron. And the group that gets picked out is the OH minus. And I'll continue on the lower border. We now see this migration occur. Very similar to the cationic rearrangements that we had been discussed not too long ago. So I go down here now to this new intermediate. I now have an oxygen bond to our carbon, and this goes by a retention of configuration. You can see the configuration is the same. So a very important note here is the migration is via retention of configuration. And the oxygen is still attached to the boron, but the boron, of course, now lost its additional electron pair, so we're back to the sextet on boron. Okay, so this is again an intermediate, but we have a lot of base left, a lot of OH minus left, and so the OH minus will come in, add onto the boron, turning it back into an electron octet. And also giving a negative charge on the boron. And now we can cleave the one of the boron-oxygen bonds, taking the lone pair here and picking this up. Like that, protonated, proton is still here, and then putting the negative charge on the ligand. minus. And then from here, I can use the water. Essentially just reprotonate the alcohol to a proton exchange with water, and that gives us our product. Okay, so this is the pathway that follows up on the oxidative treatment with hydrogen peroxide of the intermediate borane. The entire mechanism involves this interesting rearrangement after attack of the hydrogen peroxide on the boron, turning it into an electron octet. We then get the shift, the critical reaction here on the bottom left of the upper board, where you see the cleavage of the oxygen bond. That's again the driving force. And this goes via retention of configuration of the carbon-boron bond. So this bond that used to be down remains down in our new intermediate, and then it's just a hydrolysis of the boron. I wrote it out using base. There's various mechanisms you can imagine here, including different protonation steps, but ultimately you end up with a hydrolysis, an exchange reaction on the oxygen-boron bond, again taking advantage of the Lewis acidic character of the boron electron sextet that we have in some of these intermediates. And again, keep in mind that while I drew the hydrogens here, in many cases there will be another organic molecule attached here, just like the first one over here. So up on the top right, we might have in place of the hydrogens one or two additional copies of the same organic cyclohexyl group attached, because the carbon-boron bonds, the boron-hydrogen bonds react in the same way as in our borane starting material, the reagent. Okay, any questions regarding the hydroboration and the mechanism of hydroboration?